Hey, how's it going, everybody? My name is Ricardo Zapata, and I'm going to be doing combustion of toluene. So here's the balanced equation. These numbers are going to be in red, and they're going to be red throughout the entire slides, just so it's easier to take a glance at. And these are going to be in yellow. Again, it's just easier to see these numbers whenever they're highlighted. So the density of toluene is 0.865 grams over milliliters. I assume 26 degrees Celsius. This is pretty average here in San Antonio, Texas. We're going to add to 73.15 to get 299.15 Kelvin. Again, we're going to be assuming 1 ATM. Our enthalpy of formation for toluene is going to be 12.01 kilojoules over mole. And the molar mass is going to be 92.14 grams over mole. And there it is. So in order to, we're going to be calculating the volume of O2. So we're going to get 1 liter multiplied by 1,000 milliliters divided by liters. So here, liters cancel. Here's our density, our density divided by milliliters. Here, these milliliters cancels out. And here's our stoichiometry. And notice again, these numbers are highlighted in red, so it's, you guys see the balanced equation. Here's this invisible one. So 1 mole of toluene divided by the molar mass. And here, grams cancel. Multiplied by 9 moles of O2 divided by toluene, which is C7H8 and C7H8, which gives us mole of O2. And when we do this calculation, we get 84.5 moles of O2. Here's our next equation. PV is equal to nRT. And just really quick, that should be a little v. But so it's PV is equal to nRT. And we all know how to do this. We divide by P on both sides, which gives us V is equal to nRT divided by P. And this is what we're using. And we're just plugging in some numbers. So the N right here is 84.5 moles of O2. That's where we got it from. Multiplied by 0.08206 liters ATM divided by mole K. Multiplied by temperature. And here is our pressure. We're dividing right here. This is our pressure. When we do this calculation, it gives us 2.07 times 10 to the power of 3 liters. So our enthalpy of combustion. So up here we're adding, and down here we are subtracting. So we have 4 moles of H2O gas. This negative 241.02 got from Appendix G, and this negative 393.15 again from Appendix G. We're going to get 4 moles and multiplying it by negative 241.02 kilojoules. And the 7 moles, we're going to be multiplying this by negative 393.15. I know this is a plus, this should really be a multiplication. And here we have negative 9. However, it's being multiplied by 0, so this gives us a 0. And these two negatives gives us a positive output, which is 12.01 kilojoules over mole. Again, this 12.01, this comes from right here. This is the enthalpy of combustion for toluene, which gives us negative 373 times 10 to the power of 3 kilojoules. So the heat in kilojoules from combusting 1 liter of the compound. So we have 1 liter multiplied by 1,000 milliliters divided by 1 liter. That cancels out our liters. Multiplied by our density. I'm just going to put a D for density. Divided by milliliters. That cancels out the milliliters. Multiplied by moles of toluene. And this is the, let's see if I could do this little m. There we go. That's the molar mass. And that's grams. Cancels out the grams. And this 3.73 times 10 to the power of 3 kilojoules, we got it from right here, this previous slide. Divided by 1 mole of toluene. And this cancels out the toluene right here. So we get this value, 3.5 times 10 to the power of 3 kilojoules. And here's the amount of liters of the compound to generate 1 kilojoule of heat. So we get 1 kilojoule of heat multiplied by 1 mole of toluene, divided by, again, this is where we're getting this number 3.5 times 10 to the power of 3 kilojoules right here. So this cancels out kilojoules multiplied by 97.14. This is our molar mass divided by toluene. So this gives us, this cancels out the moles multiplied by milliliters. This is the density. And here the grams cancel out. And then multiplied by 1 liter divided by 1,000 milliliters. And here milliliters cancel out, leaving us with just liters, which ultimately gives us 2.85 times 10 to the power of -5. Your references and conclusions. We calculated the combustion of toluene, and the amount of heat produced from combusting 1 liter of the compound was 3.5 times 10 to the power of 3 kilojoules. Thank you.